Hi everyone. This video is going to be on the combined gas law, the big old equation that we take all three gas relationships that we've previously talked about and stick them all into one big equation so we can look at multiple changes at a time rather than just one relationship at a time. All I've done to put the information you see on your screen now in front of you is take all my information from the combined gas law section of your table T, your hotspot for equations in Regents chemistry, and just taken all that information and plopped it right there in front of you. All right. So we're going to be using this particular equation to solve big change types of problems with gases. Our P's are all standing for pressure. You're going to see a lot of different possible units for pressure. Most commonly, though, atmospheres will show up. One of the reported values for standard pressure on table A is 1 atmosphere. kPa is going to show up. 101.3 kPa is standard pressure. You may also see some less common units, things like torr or psi, pounds per square inch. But these two guys are going to be your most common, most frequent units for pressure in these types of problems. Our V is for volume, and most of the time you're only going to see volume reported in liters, like a 2-liter soda bottle, or milliliters, like a 355 milliliter can of soda. So when you're looking through these types of problems, if you see allusions to volume in either one of these units, you know exactly where you're going to be plugging it in. Last but certainly not least in this equation is our factor of temperature. And you guys know that in chemistry, we see temperature reported either in degrees Celsius or in Kelvin. However, as a result of the nature of these types of calculations, we do not ever want Celsius down here on the denominator of our equations. It can really mess things up. So we want everything for these combined gas law problems to be reported in Kelvin. So if you see degrees Celsius, you need to convert no matter what the case may be. So let's take a look at an example of that type of work where we're looking in our problem for these three variables. I'm going to start with a balloon that gets launched at STP with a volume of 6 liters. Just in that first sentence, I see two things that immediately stick out. I want to calculate the balloon's final volume if it rises to an area with a pressure of 50 kPa and a temperature of negative 20 degrees Celsius. There's a lot of apparent and hidden information in this problem, so let's pull apart what it all means. The 6.0 liters clearly references a volume, and it's the volume I started at. Let's make it V1. I want to know a final volume, so I'm calculating some kind of change. It must be a V2. Here are a final value for pressure, P2, and a final value for temperature, T2. With all these V's, P's, and T's and things changing, I know I've got myself a combined gas law type of problem, but it seems to me like I'm missing some of my information. And that's where this STP comes into play. Remember, this stands for standard temperature and pressure. And all those standard values are reported on table A of your reference table. So this T really refers to T1, and this P refers to P1. All I need to do is look up on table A what those values are. So let's do that. P1, I want to report it in kPa, so I'm going to choose 101.3 kPa from table A. V1 I know is 6 liters, and T1 is my standard temperature. So let's go ahead and pick the Kelvin value for that, because I know otherwise I'd have to convert degrees Celsius. Looking to what I changed to in my problem, P2 is that 50 kPa. V2 is what we're trying to find, so it'll be our x in our equation. And T2 is negative 20 degrees Celsius. Can't have that in our problem, so let's add 273 onto it and turn that in to 253 Kelvin. From here on out, folks, it's just an algebra problem, a big cross multiplication setup. So let's plug our numbers into the right places. 101.3 for P1, 6 for V1, and 273 for T1. And that's going to equal 50 for P2, X for V2, all divided by 253 for T2. When you're solving this type of equation, all we're going to do is throw parentheses around everything and cross multiply as we see it. 273 times 50 times x is going to be equal to 101.3 times 6 times 253. That's a huge mess of an equation to solve, but you know you want x on its own, so we've got to get rid of these two numbers here. So let's just divide both sides through by 273 times 50. And hopefully that'll get us to a reasonable value for x. Just be careful when you're plugging this mess into your calculator. Do it one step at a time. Don't let your calculator ruin you with order of operations. So do what's most comfortable for you to be able to make sure that all of this is getting divided by all of this and nothing's being left out or done kind of at the end as multiplication instead of division. When I plug this into my calculator, I get 11.265, which I'll round to 11.3. And I know that my units on that have to match my original units for volume. So let's make it 11.3 liters. And that's that. Because I converted to Kelvin, I got a measurement that seems to make sense. Let's take a look at a second problem. After being left on, a light bulb's internal temperature increases from 25 degrees Celsius to 90 degrees Celsius. I see immediately a T1 and a T2 in this problem. If the rigid bulb, that must mean it can't change shape, so volume probably isn't going to be involved in this problem. If it's beginning at standard pressure, you guys know that this is a hidden value. There is a standard pressure and it's reported on table A. I want to calculate its final pressure, its P2, and I want it done in atmospheres. Because I see changes in temperature, pressure, and or volume, I know this is a combined gas law situation, so I'm going to write out my equation and then just plug and chug from what I see in the problem. But like we alluded to here, volume isn't mentioned at all. It's not changing. There is no V1 or V2, so let's just scribble it out so that we don't have to deal with it. We're left with a simple relationship between pressure and temperature. From my problem, P1 is just standard pressure. I want it ultimately to be in atmospheres, so let's select 1 atm from table A. T1 is 25 degrees Celsius, but I can't have that Celsius going on, so let's add 273 and turn that into 298 Kelvin. My P2 is what I'm looking for, so it's my X. And my T2 is 90 degrees Celsius, but let's add on that 273 to get us up to 363 Kelvin. Once you've got all your variables picked out, it's just a plug and chug. Plug in 1 for P1, 298 for T1, X for P2, and 363 for T2. If I cross multiply, 298 times X is going to equal 363. To solve for that, I'm going to need to divide both sides by 298, and that gets me to a value of X being equal to 1.2-ish. When I need to pick my unit, it told me to pick atmospheres. That matches what I picked for P1, so let's label that as 1.2 atmospheres. The pressure went up when the temperature went up. That checks out for me. So as you are looking at these problems, first, look at all the information given. Pull it out. Is it a temperature? Is it a pressure? Is it a volume? Make sure you can be using this combined gas law equation. Then make sure that you're picking out appropriate values for pressure, temperature, and volume from your problem. You're converting all temperatures to Kelvin, and you're just being very careful when you cross multiply, and this should be a nice, easy little math scenario for you guys.